Today we're going to start our discussion of antiderivatives and indefinite integrals. If I give you a function and call it capital F is considered an antiderivative of little f on an interval if the derivative of capital F is equal to little f for every x in the interval. I'm going to explain this in a little bit more detail. Basically, an antiderivative is the equation you would get when you do the reverse or backwards operation of a derivative. When we're doing derivatives, we're getting a general equation that you can use to find the rate of change or slope of a function. Antiderivatives give you a general equation that you can later use to find the area under a curve. This is going to give us an exact equation that we can use to find the exact area under a curve. Now this general equation we're going to get is called the antiderivative, like I said, or it's called an indefinite integral. Again, the result you're going to get for the next lesson is an equation. Note that definite integrals are what we did last week, where I gave you a starting and an ending x value. We don't have starting and ending points today. Today we're only going to get a formula. So let's explore this idea a little bit more because there can be many antiderivatives of a function. Let's start with an example. You have this in your notes. What happens when you take the derivative of 3x to the fourth plus 2x cubed plus 5x plus 3? Go ahead, take a minute. What do you get? Write it down. I hope you got 12x cubed plus 6x squared plus 5. Now let's look at a different function. What happens when you take the derivative of 3x to the fourth plus 2x cubed plus 5x plus 6? Go ahead, take a second. Take its derivative. I got 12x cubed plus 6x squared plus 5. Wait a second. You get the same derivative. So when we go backwards from the derivative, if I want to take this red equation and this red equation and go backwards to these two originals, what do I add on to the end? Is there a 6 on the end? Is it the one with the 3 on the end? Which of these original functions is the actual antiderivative? Will the real antiderivative please stand up? Which original problem is the answer? We have to decide which one. Now, there's a way to handle this. In general, we're going to go ahead and add on a c to every antiderivative we take. Whenever you go backwards, you must never, ever, ever, ever forget the c on the end. C holds the place of the number on the end that we're not certain of, like in the last example, a 3 or a 6. We'll eventually learn how to find out what c is, but in the meantime, we're just going to hold a spot for it so it doesn't feel left out. It's going to, again, represent that constant on the end of an antiderivative. Never, ever, ever, ever forget to add c onto the end of every antiderivative or indefinite integral that you do. And if you're wondering, yes, anytime you do this on a test or a quiz, I will take all the points off. I will mark this 100% wrong if you forget the c. Here's why it's so important. There's a graphical interpretation of what's going on when we do the antiderivative. If I get an antiderivative and the equation is x squared plus 2x, x squared plus 2x, x squared plus 2x, is it going to have a 4 on the end, nothing on the end, or a negative 3 on the end? Here's what the graphs of each of those functions look like. It really depends on what this number at the end is, because it might mean the graph is up here, or down here. Here's another one. If the antiderivative of a function is x cubed over 3, what number is on the end of it? Because it'll make the function or the answer look different. So we have a formal theorem about this c. Again, if we take this capital F, and that's an antiderivative of a little f, and then I have this g is also an antiderivative, then g and f only differ by this plus c. So now we can put that into a definition. This is the definition you need to have memorized. If I have the notation integral of a function to go backwards from this function to its indefinite integral, I change it to a capital F, and I always make sure I add a plus c on the end. C is any number. We're going to figure out in, again, another lesson what c is. But what that denotes is the family of all the antiderivatives, like you saw on the previous page. Again, this is the same definition that we used on the previous page for the antiderivative, but it has a fancy integral notation now. Now, how do we calculate these integrals? What is the shortcut? It's really easy. We're going to use what's called a table of integrals. Now, you're going to get a new formula card, like the formula card I gave you for derivatives. You're going to get a new formula card for integrals. When you get it, you're going to go ahead and add these and only these formulas to it. The shortcut, if you have the integral of 1, is just x. That would look the same as the integral of just dx. Again, it'll give you x. Now, this is true if you have any number here. So the integral of 2 is 2x. The integral of 3 is 3x. The integral of 4 is 4x. So if it's just a number, it's just that many x's. And of course, plus c. I'll show you more detail in the examples. If you have an x to a power, remember for derivatives, we brought the power down and subtracted 1. Well, now for integrals, you're going to do the exact opposite. You're going to add 1 to the power, and instead of multiplying, you're going to divide by the new power, always remembering a plus c. You have to be careful. The original r right here cannot be a -1. That's going to be a different formula we're going to learn later. I won't give you any that's a -1 right now. They'll all be other numbers besides -1. So what I'm going to do is show you how to use them in the examples. But before I do, as with most things that we work on in calculus, there's some theorems that you need to know. So the first theorem right here is the integral of the derivative of a function. Now, integrals and derivatives are inverse operations. When the integral is on the outside, you're going to have a c at the end. But notice this f of x is the same as this one. So basically, integral first and derivative, they cancel each other out. But because the integral was first, you need to make sure there's a c on the end. If the derivative is first, then the integral symbol. Again, they're going to cancel out, but you do not need a c because the derivative on the outside would take the derivative of c. Since c is a number, its derivative is 0. Now some straightforward ones. If you have a constant in front of a function, remember constants go along for the ride in derivatives, in limits, in sigmas, so this c can just come out front. And again, this theorem says that constants just go along for the ride. If you have the integral of two functions added, you can break them up separately. So again, you can break them up over addition. And the same thing is true for subtraction. So now it's time for some examples. Here's our first example. Now again, you would need a table of integrals for this. I'm going to go ahead and post one on Google Classroom. I'll take a picture of the table that you're going to get when you see me next. And you can use that to do your homework assignment. But for now, I'm just going to go ahead and show you these, and we'll do them by example. So for this first one, the integral of 5x cubed plus 2 times the cosine of x. You are going to go ahead and do every term individually. So I'll take care of this 5x cubed first. When I did derivatives, I moved the power down and subtracted 1. Well, now for integrals, you're going to add 1 to this power, make it a 4, and divide by the new one. So the 5x comes down, add 1 to the 3, and you get 4, and then divide by that new exponent, 4. And there you go, that's the derivative of 5x cubed. Now 2 is a constant, so that goes along for the ride. You just carry that down, and you can look up on your integral table. Again, I'll give that to you when I see you next. You can go ahead and print it offline if you'd like, off of our Google Classroom. I took a picture. And you can look on there that the integral of cosine is just sine. And now you're done. The only thing you really need left, as you will need with every integral, is plus c, in case when I go backwards, there was a constant on the end. Let's look at another example. Here's example 2. Now I've only really taught you rules for exponents, and anything else that's on that table you can go ahead and use. But there are no real radical equations on the table, and this one is on the bottom. So sometimes when you're working on integrals, you're going to have to work backwards and make sure that you do some pre-calc rearranging first before you take the actual integral. So what I'm going to do before I actually take any integrals, before I do anything new, is I'm going to perform some pre-calc on this. Now the 8t cubed, that has nothing wrong with it, it can stay. But I have to rewrite this t with the square root as t to the 1/2, so I can make it a power. You want to basically do the power rule we've been doing with derivatives in reverse, so you have to make things look like something to a power. So that means I'll do the same thing with this one, and I'll make it t to the negative 3, always with our parenthesis dt at the end. So now I'm ready to go ahead and take the integral. So I will add 1 to all of these powers and divide by the new power. So I have my 8t, it'll now be raised to the 4th power, and I'll divide by the new power, 4. Then I'll have my 6t, raise it to the add 1, makes it 3/2 power, divide by that 3/2. And then I'll take this t to the negative 3, add 1, makes it to the negative 2, and I'll divide by negative 2, always adding a plus c to the end. Now I do want you to simplify things like this, so I'm going to go ahead and go over that now. If I take this original equation right here, I can take the 8 and divide by 4. Again, this equation on this slide, I just copied and pasted from the last slide, so I didn't change anything. My next step, again, would be to take 8, divide it by 4, and get 2. t to the 4th stays the same. Now to take care of this one, you're going to leave the 6 in the problem, but you're going to take this 3/2 and flip it and multiply. So basically, again, you have 3 over 2 on the bottom. You're going to multiply this entire top by 2/3, and so that'll look like this. 2/3 times the 6t to the 3/2. And then we can simplify this further. Again, what I did was I took 3/2 in the denominator, flipped it, and made it 2/3 with a multiply. And then for this term, I like all my exponents to be positive. That's how I want you to leave your answers in this section. So I brought this negative in front. I left the 2 on the bottom, but this t to the negative 2, I moved it to the bottom to make it t squared, so that that negative 2 became a positive 2. And now this one's as simple as possible, bringing down the plus c. The last thing I have to do is work on this thing in the front. So my 2t to the 4th got carried down. 2 times 6, that's 12, divided by 3 gives me the 4. And then I copy down what's left. And this is how you'll see the answers in the back of the book and how I expect you to answer questions when I give you a quiz. Let's work on another one. Remember, when you're doing these, you can only use the equations on the equation card, on the formula card, again, the one that I took a picture of and is posted on Google Classroom. So what that means is something like this, a very complicated problem, is not on your card. There's no other way to solve it than to do algebra first. So I'm going to go ahead and take this squared on top and FOIL. So I'm going to expand the top. Squaring the first term gives me x to the 4th, then a minus 2x squared, then a plus 1. Again, I FOILed the top. Now what I need to do is break this up into 3 individual terms by giving the denominator to each of these numerator pieces. So I'll give x squared to that one, and that one. And breaking them up individually, here's what I'll get. I'll have the integral of x to the 4th over x squared minus, here's the 2x squared and the x squared on the bottom, and then the last one, 1 over x squared. And now I have to reduce each of these fractions. So first, x to the 4th over x squared reduces to x squared. Then the x squared and the x squared here cancel, so I have a minus 2. And then like in the last problem, anything in the denominator, I have to move it up to the numerator and make the exponent negative. So this is x to the negative 2. Now this is in the proper form for an integral. So I will do each one separately using our new power rule. Raise the power by 1 and divide by the new power. So I'll have x cubed divided by 3 minus 2 times x. This was that first theorem I talked about you adding to your formula card when you get it. If it's just the integral of a number, the answer is that number times x. You have to add the x's back in. And then for this one, I'll add 1 and divide by the new power. So it'll be x to the minus 1 divided by minus 1. And I do realize now that I have a typo. This is a plus, and this should be a minus. Should not be a minus, so that should be a plus. So we're going to have to go ahead and fix that later on. So plus c. So now I just recopied these 2 terms. And again, I do have a typo here, so please fix this in your notes. This should be a plus. This then should be a minus. And now my problem is complete. What I did from here to here, again, this should be a plus. this should be a minus, is I moved this x down to the denominator. So this answer, again, please fix it. It should be x cubed over 3 minus 2x minus 1 over x plus c. Last example. Sometimes factoring or multiplying something out or simplifying it with powers works. And you can go ahead and do that right away, and you can make any negative powers positive, positive powers negative, whatever you have to do to make it look like you can use the power rule. But sometimes with a trig function like this, 1 divided by cosine cotangent, that's not exactly on your formula card. Cosine might be there, cotangent might be there. You have to make this look like something on that formula card. So you're going to have to do maybe some pre-calc rules with trig, using identities or something like that first. So you have to get used to that. You have to practice it. You'll get there as you work on more problems. That's why you're assigned 1 to 41 the odds. I want to give you quite a few to practice with. Here's some things you need to start looking for. If I do 1 over cosine and 1 over cotangent, I basically can use the identities to turn that into 1 over cosine is secant and 1 over cotangent is tangent. Okay, well, when you look at your formula card, secant, tangent together, remember those are BFFs from derivatives? Those together are on your formula card. It's one of the numbers. Look for it. Secant tangent has a formula, and it's just the secant plus c. So this problem is only a 3-step problem because I was able to look for 1 over cosine and 1 over cotangent and just find a formula on the formula card. So after you simplify, if you can't use the power rule, you have to look at your formula card and see if something matches. Everything will in this lesson and in this homework assignment. So always remember to try pre-calc before you integrate and use any of the formulas on the formula card. Some things you might want to try are factoring, multiplying something out, rules for trig identities, maybe like sine squared plus cosine squared is 1 of those things. So as you're working on your assignment for this section, take out your derivative note card, look at the front of it, and there's a whole bunch of trig stuff that you might want to use there.